Your computer is behaving strangely. Something is running slower than it should. A program freezes and unfreezes for no reason. A browser tab eats more memory every hour. Your fan is running at full speed when you're not doing anything intensive. Someone tells you to restart it. You restart it and everything works fine. You never find out why. Here is what actually happened. A computer runs software. Every program that runs on your machine requests memory from the operating system to work with. RAM, the fast-working memory your computer uses to hold information while it needs it. When a program closes, it is supposed to hand that memory back so other programs can use it. Most of the time, in most programs, this works correctly. But not always. Memory leaks are one of the oldest bugs in computing. A program requests memory, uses it, and then, because of a coding error, an unexpected sequence of events, or a conflict between two pieces of software that were never tested together, it does not release that memory when it is done. The memory sits there, occupied, allocated, but unused, like a parking space that has been reserved but is sitting empty. Run enough programs, trigger enough edge cases, leave the system on long enough, and the accumulated leaked memory can become significant. The system starts running low on available RAM. To compensate, the operating system begins using the hard drive as overflow memory, a technique called paging or virtual memory. The hard drive is vastly slower than RAM. Everything slows down. The computer starts behaving exactly as yours is behaving right now. A restart wipes the slate clean. Every program is closed. Every memory allocation is cleared. The leak is not fixed. The bug in the code is still there, but it is flushed. The system starts fresh. The same logic applies to the operating system itself. Windows, macOS, and Linux all run dozens of background processes you never see. They manage hardware drivers, monitor the system, handle updates, and run services that application programs depend on. Some of those background processes have their own memory leaks, their own accumulated state, their own slowly growing problems. They accumulate over days and weeks of uptime. There is a second category of issue beyond memory, and it is called state accumulation. When software runs, it writes temporary files, session data, configuration changes, and logs. It records its current state to disk so it can resume where it left off. Some of this is done carefully. Some of it is done sloppily. Files that are supposed to be temporary linger indefinitely. Configurations that should reset on close don't. The longer a system has been running, the further its current state has drifted from the clean, tested state the developers expected. A restart clears a large portion of this. Not everything persists through a restart. Some files are designed to survive, but enough is cleared that the system returns to something close to its original state. The longer a computer runs without restarting, the more this state divergence accumulates. Software is tested over short periods. Real computers are used for months without stopping. The gap between the tested environment and the live environment grows. Servers, the computers running websites, databases, and back-end services, can run for years. Engineers managing them use careful monitoring, automatic process restarts, and detailed logging to catch problems before they require a full system restart. A planned server restart requires coordination, backup failovers, and timing to avoid disrupting users. A restart of your laptop requires you to click a button. Modern operating systems are significantly better at memory management than their predecessors were. Automatic restarts during software updates, improved garbage collection, and better process isolation mean that a modern machine running modern software genuinely needs to restart less often than it once did. But the fundamental architecture has not changed since the first operating systems were designed. Multiple programs share a pool of memory. Each program is responsible for releasing what it uses. When programs fail to do that correctly, the pool shrinks. When the pool shrinks far enough, the system degrades. Turn it off and on again. It is not a joke. It is not an admission of ignorance. It is the fastest way to flush the accumulated errors of a system that has been running longer than its code expected. The restart is the fix for a class of problem that was easier to flush than to prevent. Now you know.